Welcome to Data Science for Everyone. So this is the work of 8 strenuous months because volcanoes are actually pretty hard to predict. I'm going to go ahead and try to get the preliminary information out as soon as I can because it's a very long video. But before we talk about how I predict volcanoes, we should talk about why they erupt. Now I'll give you my predictions for eruptions at the end of the video. Earth's volcanoes are the result of magma rising through the planet's mantle, but have you ever wondered where these roots run? UC Berkeley created the first ever detailed 3D map of the Earth's interior by studying the path of seismic waves. Volcanoes can be predicted about a week or two out because of seismic activity, but my approach by taking every eruption in recorded history as a time series is based on the assumption that past eruptions will predict future eruptions. So, what was the biggest eruption? There is one M9 event known so far, the Fish Canyon Tuff, with an erupted magnitude of 9.2. There is a 1% chance of an eruption of this scale in the next 7,200 years. So why do I think my idea of using eruptive history alone has any merit? Dr. Yuri Dubik, a Russian volcanologist who has studied past eruptions, on the Kamchatka Peninsula for 35 years, says there is no doubt that the eruptive history of a volcano is the main key for long-term prediction. Variables you could look at would be the physical remains of previous eruptions, mapping old lava flows, pyroclastic deposits, and other volcanic debris distributed around the crater can reveal much about the timing, type, direction, and magnitude of previous blows. But you'll see that most time series models make an assumption that more recent events are more directly responsible for future events. Is this true for volcanoes, or is this a very, very long cycle we can observe? Research shows active volcanoes can be thought of as moving toward a crisis point. The seasonal changes in the stress experienced by the Earth's crust make it slightly easier for systems to reach a crisis point at certain times of the year. This results in seasonal volcanism. Seasonal patterns of volcanic activity are also observed in long datasets from single volcanoes which erupt repeatedly, such as Sakurajima volcano in Japan, when the eruption rate peaks in the month of November. To find out why the seasonal pattern occurs, the team ran statistical tests that ruled out any systemic link with Earth tides, deformation of the solid Earth by movements of the sun and moon. The research believers the research believes the culprit is the major driver of seasonal cycles at the Earth's surface, the global water cycle. These annual changes in the Earth's shape can be seen with both satellite laser ranging and ground-based global positioning system measurements, and are vertical movements of only centimeters. These very small periodic movements are probably too small to trigger volcanic eruptions. So, other ways you can predict a volcano: earthquakes. So there's ground deformations when a volcano is about to blow. One thing that I found interesting is volcanoes that share common magma reservoirs can sometimes trigger unrest at each other. Some individual volcanoes or events are considered to be part of a larger volcano complex. For example, Tavrovara and volcan cones within the Rabaul caldera in Papua New Guinea that erupted at nearly the same time in 1994. So there are some volcanoes that don't stop erupting, which was one of many wrenches thrown in this forecasting. Overall, 47 volcanoes were in continuing eruption status as of 15 December 2023. An eruption marked as continuing does not always mean persistent daily activity, but indicates at least intermittent eruptive events without a break of 3 months or more. There are typically 40-50 continuing eruptions, and out of these, generally around 20 will be actively erupting on any particular day, and this trait makes it hard to predict future eruptions, so I might try building a whole different model for just shield volcanoes. So if I had access to the thermal satellite, I would try spatial temporal forecasting, or we could try temporal graph neural networks. There is ongoing research to make gravity sensing satellites, but I don't have access to those satellites. So I built this web scraper. I use Selenium because it's for browser navigating. When you're using automation, and you can even use it in conjunction with PyAutoGUI to fool some cache fuzz, but you didn't hear that from me. So I didn't use all these variables because a lot of the emissions data is incomplete, and a data set with a lot of missing values is useless for time series forecasting. So We're about to get technical. Why would you want to learn time series and how is forecasting different from deep learning and machine learning? So time series are pretty universally applicable. MOFC is known worldwide for organizing and running the Makudrakis competition, also known as the M competitions. These are a series of open challenges aimed at improving the theory and practice of forecasting conducted for the last 42 years, intending to evaluate and compare the accuracy of different forecasting methods. Like M5 was about using hierarchical forecasting. So your first model is probably going to be machine learning. It's probably going to be nice and neat linear regression. When running a linear regression, the assumption is that all the observations are all independent of each other. In a time series, however, we know that observations are time dependent. It turns out that a lot of nice results that hold for independent random variables, like the law of large numbers and central limit theorem, holds for stationary random variables. So by making the data stationary, we can actually apply regression techniques to the time-dependent variable. So the go-to model for time series is ARIMA, and if you have seasonal components, you would use SARIMA. So ARIMA accounts for the differencing in its order of PDQ. Let's go over some concepts we need. Unit root is a feature of time series where a shock or change in one period has a permanent effect on all future events. It's like a ripple that never fades away. A stationary process is one where the unit root is removed, so shocks or changes gradually fade over time like ripples in a pond. A classic example of a unit root process is a random walk, where each step is influenced by the previous one, leading to unpredictable long-term behavior. Those would be better modeled by a hidden Markov model. Co-integration. When two or more unit processes share a long-term relationship, they are said to be co-integrated. This is going to throw off your forecasting. You get more accurate forecasting by detrending and deseasonalizing your data. If a time series has a unit root, a non-stationary trend, directly modeling it can lead to biased and unreliable forecasts. This is because the trend keeps increasing or decreasing indefinitely, making future predictions unrealistic. Stationary tests like the Dickey-Fuller test rely on assumptions about the distribution of the error terms. Zeros can affect the validity of these assumptions, potentially leading to unreliable test results. Here are some strategies to handle zeros when aiming for stationary. So there's the specialized transformation, like a Boxcox transformation. There's robust stationary tests, like the KPSS test instead of the ADF test. There's model selection. Depending on the nature of zeros and your modeling goals, you might choose models that can handle non-stationary data, like ARIMA with integrated differencing and arch models. Or you could try aggregation. If the time gaps are not too large, you might want to aggregate your data to fixed intervals like daily or weekly. This creates a more regular series but might lose some high frequency information. But for our model, we can't just cram different traits of volcanoes into one X variable. So if we went with aggregation, we would have to use count data and lose some of our X variables. But that's a whole new problem that would be better suited for poisson regression, which I'm going to try. And so the next thing, I have an irregular time series. When I fill in all the dates without recorded observations, like a day where a volcano didn't erupt, this is how many rows I get. So this is just going to get me an overflow error in most models like ARIMA and Profit. So I just leave the eruption observations in. I don't include any days where there was an eruption. This makes inconsistent intervals. The lack of consistent time sets between data points creates challenges for traditional differencing approaches. Differencing is how you can make a time series stationary. And there's also days with multiple eruptions, and this makes it hard for most models because they're expecting one observation per interval. If I do something like average the VEI, then it loses data on the different volcano and rock types. With multiple observations per frequency, differencing wouldn't effectively remove seasonality or trends if they occur within the same time window. I would have to do something like make a time series for each volcano, which make the time series extremely sparse, and without some big data techniques will always lead to a memory error. So here are some alternative techniques for irregular data. time series kernel smoothing. This technique smooths the data using kernels, potentially reducing the impact of irregular spacing, allowing you to analyze trends without strict differencing. Functional data analysis. This approach treats the time series as a function and uses techniques like basic function expansion to model the underlying trend and seasonality, accommodating irregular spacing. Change point detection. Techniques like PELT, pruned exact linear time, or CumSum, cumulative sum, can identify potential changes or breaks in the time series, which might be more relevant than lags for capturing patterns in irregular data. Which you should ask yourself, are the gaps random or do they follow a pattern? Are they just missing data points? Depending on the nature of the irregularity, random gaps, you might want to try point process models. These models specifically focus on analyzing the timing of events, including gaps between events. Pattern gaps. If the gap follows a pattern, like weekends or holidays, you might be able to use seasonal ARIMA, including seasonal components in the model to capture the cyclical patterns of event occurrences. And there are two problems for volcano data when using those techniques. It's that recording volcanoes, like scientifically, only started recently, and we can see this in the increasing frequency of observations. So that's a case of correlation, not causation, because you might think there are more volcanoes erupting, but no, there were just more recording of them. So how do we determine if a time series is stationary or not? We can use the augmented Dickey-Fuller test. Similar to a t-test, we set a significance level before the test and make conclusions on the hypothesis based on the resulting p-value. The null hypothesis is the data is not stationary. The alternative hypothesis is the data is stationary. If the p-value is greater than the significance level, then we can say it is likely that the data is not stationary. The result of the ADF test itself. Here's what the 5 elements of the result table represent. First one, the ADF test statistic. The second one, the p-value associated with the test statistic. The third one, the number of lags used in the ADF regression. The fourth one, a dictionary containing critical values for different significance levels. And finally, the value is specific to the add Fuller function and not directly interpretable for stationary assessment. I got these functions to investigate whether a time series is stationary or not and what lags will make it stationary, but you can also focus on removing trend and seasonality to achieve stationary. So let's go with STL decomposition. The STL is an acronym for seasonal and trend decomposition using LOES. LOES is a method for estimating nonlinear relationships. So in order to do seasonal decompose and avoid a value error, I just use. So what are we looking for in these plots? In the trend section, you want to identify the direction of the trend. You want to assess the linearity of the trend. A nonlinear trend might indicate a need for more advanced decomposition techniques. The residuals. Ideally, the residuals should be close to white noise, meaning it has no discernible patterns or trends. Random fluctuations around zero indicate good decomposition. If the remainder exhibits patterns or trends, it might suggest additional components or insufficient decomposition. You can see in the trend in the residuals that there are more observations recently. And in the seasonality, you want to identify the period of the seasonal component, you want to analyze the amplitude of the seasonal component, and you want to look for any changes over time. But a better way of seizing the seasonality is using a periodogram. So, insights from the periodogram can guide you to selecting the appropriate models for analyzing your time series data. For instance, if the periodogram suggests strong seasonality, you might want to use SARIMA or SARIMAX. How do we interpret a periodogram? So the x-axis represents frequency measured in cycles per unit time. The y-axis usually represents the power or spectral density of the signal at each frequency. This can be in various units depending on the specific calculation method. Higher values on the y-axis indicate strong power at that frequency. In some cases, there might be multiple peaks or broader humps in the periodogram, suggesting the presence of multiple periodicities or less well-defined cycles. So when using seasonal decompose, It's important to remember that seasonality doesn't necessarily mean the four seasons. It could be a shopping season, a peak season. Using this using MSTL accounts for multiple seasonalities. And we can use the periodogram to see what period we might want to pass to the decomposition periods. The period of each seasonal component period passed to SDL would be like 24 times 7 for the weekly period. We can also try, if you have seasonality, the seasonal augmented Dickey-Fuller test. So this extends the ADF test for stationarity, allowing you to specify a seasonal period and test if the data exhibits seasonality after accounting for trend and differencing. But I don't actually need to make it stationary because I'm using a neural network. So I'm using PyTorch instead of Keras. PyTorch and machine learning, it is generally assumed that training samples are independent and identically distributed. As far as the sequence data is concerned, this isn't always true. If the sequence values have temporal dependence among them, such as time series data, the IID assumption fails. So in PyTorch, the computation graph is built on the fly during the forward pass. And so this allows for more dynamic and flexible model definition. So we're just going to take the days of eruption. And I did some data pre-processing to put it in a time series data set. So this is from PyTorch forecasting, and what it does for us is it scales and encodes the variables, it normalizes the target variable, it officially converts time series to impanded data frames to torch tensors, and it holds information about static and time varying variables known and unknown in the future. And also from my regular time series, it has the allow missing timestamps argument, which is very important. So if you see the imbalance in my value counts, that's also not good for forecasting. In basically every kind of regression, machine learning, you should have balanced groups. So if you have imbalanced groups, you might want to use adaptive sampling techniques like reservoir sampling or oversampling or undersampling to balance the representation. When using weighted samplers to address imbalanced data, the default collate FM might not properly handle the weights within each batch. A custom function can ensure the batch composition reflects the desired weighting of different classes. Or you could try oversampling the minority class. This involves artificially increasing the number of samples in the rare class to balance the distribution and avoid bias towards the majority class. Or you could use class weights. Assign higher weights to the minority class during model training to balance the impact of each class in the loss function. So, sequence modeling algorithms of LSTM come in two flavors, stateless and stateful, depending on the architecture used while training. The way these two architectures differ in the manner in which the states, the cell and hidden states of the model are initialized in the training process from one batch to another. The way these two architectures differ is the manner in which the states, cell, and hidden states of the model corresponding to each batch are initialized as the training progresses from one batch to another. This isn't the same as the parameters or the weights, which need to be propagated through the entire training process. There's usually a lot of confusion between the cell state and hidden state. The cell state is meant to encode a kind of aggregation of data from all previous time steps that have been processed, while the hidden state is meant to encode a kind of characterization of the previous time steps data. It's important to note that the hidden state does not equal the output or prediction. It is merely an encoding of the most recent time step. As said, the hidden state at any point can be processed to obtain more meaningful data. You can use the nn.lstm cell to modify the inner mechanisms that are abstracted away when you use the LSTM class. You can manually define the number of layers, loop through them, and potentially apply custom operations, like additional transformations between each cell, like maybe you want to change the forget gate. But usually you only need that if you're doing research or specific architectures. The LSTM class is great. Sequence data such as time series contains non-IID samples. We mentioned that before, so it will be a good idea to assume that the divided batches are independent when they are actually not. Hence, it is intuitive to propagate the learned states across the subsequent batches so that the model captures the temporal dependence not only within each sample sequence but across batches too. So, Detaching the encoder states prevents gradients from flowing back through the encoder during decoder training. It addresses vanishing and exploding gradients and overfitting issues. When you initialize the decoder states with zeros, like H0 and C0, these states are not connected to the encoder's computational graph. They are essentially new tensors with no history or gradients associated with them, so it has the same effect as using detach. The encoder-decoder model is what we're using. It consists of two networks. The encoder network learns a representation of the input sequence that captures its characteristics or context and gives out a vector. This vector is known as a context vector. The decoder network receives the context vector and learns to read and extract the output sequence from it. So this model uses an iterative decoder and gets a context vector for each time step. Iterative decoders might struggle with capturing very long-term dependencies within a time series, especially when dealing with long sequences. The attention function calculates the context vector and then concatenates it with the decoder input before feeding it to the decoder LSTM later. By concatenating the context vector with the decoder input, the model incorporates information from the relevant encoder outputs into the decoder's processing at each time step. This allows the decoder to generate outputs that are influenced by the entire encoder sequence, not just the current decoder input. It sounds like teacher forcing. It's not. I have a different model that uses teacher forcing. The decoder's hidden state calculates attention weights over the encoder outputs. These weights are used. So let's switch to the other model. We need to think about long-term dependencies. What are long-term dependencies? It's when events that are older have more influence. ARIMA models are inherently autoregressive. They predict future values based on a weighted sum of past errors and past values in the time series. This approach works well for capturing short-term dependencies where recent observations have a strong influence on future values. However, for long-term dependencies, the influence of past observations might fade over time, making it difficult for ARIMA to capture them effectively. You can change the order, I believe it's the P, to try to make up for this, but that only goes so far. So if iterative decoders might be bad for capturing long-term dependencies, and ARIMA is bad too, what is the right approach? Well, time series dataset isn't flexible. It already has its own batch sampler. So how else can we use a sequence to sequence model without a time series dataset? So without the time series dataset, this is how I identify the time series for the model. This function adds a new feature to the data that identifies the time series index for each data point. It calculates the total number of time series and adds a new column to the encoder and decoder inputs. This new column contains a value representing the time series index normalized between 0 and 1 for each data point. So this can be useful for the model to learn relationships between different time series. Now let's look at how my attention mechanism is different. This one uses two linear layers to project both the decoder hidden state and encoder outputs to a new hidden space before calculating a similarity score. The linear layer allows the model to learn a more complex, nonlinear relationship between the decoder and encoder representations, potentially leading to better performance. So the code concatenates the decoder hidden state with each encoder output vector along dimension 2. This creates a tensor where each element represents the interactions between the decoder state and specific encoder output. A linear layer with a 10 activation function is applied to this concatenated tensor. This step learns how well the decoder's current state aligns with each encoder output. Another linear layer applied to further process the outputs, resulting in a single score for each encoder output. So far, we have dealt with pointwise predictions where the model directly predicts each new time series value. An alternative is probabilistic forecasting, which has the model learn the distribution to sample each point or prediction from. This is done by having the model output the parameters to a distribution such as the Gaussian, which would be the mu, a mean and sigma standard deviation, and then the actual point is sampled from this distribution. This is an efficient way to avoid the problem of learning instability caused by noise. In point-wise forecasting, the model will attempt to predict this noise, which by definition is not predictable. Probabilistic or stochastic forecasting also allows for sampling multiple varying trajectories. Pointwise forecasting assumes a normal distribution of errors, which might not be the case for non-normal data. This can lead to underestimating the actual range of possible future values and potentially misleading confidence intervals, but it's still good to try because probabilistic forecasting allows you to sample multiple possible future trajectories from the learned distribution. This helps visualize a range of potential scenarios and their probabilities. So here's the functions we need for probabilistic forecasting and how they work. This static method extracts the mean and standard deviation parameters from the model's output in a probabilistic setting. It uses soft plus activation to constrain sigma to positive values. It includes error handling using try except to handle cases where the output shape might differ. Then, this static method samples from the model's output distribution if it's probabilistic. This trick introduces a reparameterization, how do you even say that? Which is a way to rewrite a random variable from a complex distribution to a form suitable for backpropagation. It uses the reparameterization trick with normal distribution mu sigma for probabilistic outputs. For deterministic outputs, it simply reshapes the data. So now let's talk about teacher forcing. I'm still using an iterative decoder, but now I have teacher forcing. In teacher forcing, the decoder in a sequence-to-sequence model is taught by feeding it the correct target element from the ground truth as input at each training step. This helps the decoder learn the mapping between the encoder output and the desired output sequence. It also has a drawback called exposure bias. Since the decoder always sees the correct target element, it might not learn to generate the correct outputs on its own, especially when encountering unseen inputs during testing. So that's why we have scheduled sampling to introduce randomness during training. With a certain probability, the decoder is fed to its own previous prediction from the last time step as input instead of the ground truth target element. This forces the decoder to learn to rely on its own predictions and improve its ability to generate sequences even without always seeing the correct targets. So, scheduled sampling decay defines the rate at which the probability of using teacher forcing decreases over time during training. Inverse sigmoid decay defines a function that calculates the probability based on the current training step. It uses an inverse sigmoid function which starts high and gradually decreases towards zero. Calc teacher force prob is an instance of the inverse sigmoid decay function specifically configured with the scheduled sampling decay value. By gradually decreasing the probability of teacher forcing over time, the model is weaned off from relying solely on the ground truth and learns to generate its own outputs more effectively. So now let's go to the actual training. Each epoch we cycle through the training data batches and perform the following steps. To computing the gradients of the loss for the model's parameters, we perform a backward pass. Utilize the optimizer to update the model's parameters. I use softmax for classification in the last step of the LSTM forward pass. So I have a specific loss function for classification too. That's cross entropy loss. It expects the input to be a probability distribution over classes for each sample, which is what softmax produces. If you're wondering what unsqueeze and squeeze does, the unsqueeze method adds a dimension of extent 1, unsqueeze as it is a new 0th dimension. Now you have a batch of 1. By squeezing, we're taking advantage of the fact that any dimension of extent 1 does not change the number of elements in the tensor. So, we don't have the VEI of every volcano that erupted in 2024. Remember how I said a lot of them are continually erupting and that's hard to predict? That's what messed this all up. So, trying to predict the VEIs of 2023 were pretty lackluster, so let's try to switching to predicting just whether or not a volcano erupted in January. However, this increases our number of zeros, which makes our target variable sparse. So I change my output size to 1. We hit the ARIMA to get the most likely option from the class probabilities, and we got all zeros. So let's try a foundational time series. I have a whole video on foundational time series, but let's just use Facebook's profit. Patching, which is used in most foundational time series, involves creating multiple short-term forecasts and stitching them together to form a longer-term forecast. This approach can introduce errors at the seams where patches are joined. Direct forecasting is what Profit uses. It avoids that issue by directly applying the model to the entire forecast horizon, leading to potentially more accurate forecasts, especially for longer horizons. I have to pre-process the data because it expects it to be labeled like this. Can you use differencing to deseasonalize in Profit? Well, it's not necessary. It is part of the model to assess seasonality, but you can include it as a regressor with Fourier terms. If the optimal Fourier order seems to be very high, it might indicate that your data has additional complexities beyond simple seasonality. So you might want to explore other factors that might influence your time series. We can see how confident our model is in its predictions by plotting it. It's pretty wide. A narrower confidence interval indicates that your model is more precise in its predictions. It suggests that the true value is likely to be closer to the predicted value with less uncertainty. And you can find the forecast in the object of Profit by looking at the y-hat key. It represents the point forecast, which is the single most likely value predicted by the model for each future time step. So let's move on to SARIMA. I didn't really use SARIMA or VARMAX because using an autoregressive model with all the issues we talked about, the sparse target variable, the irregular time series, it wasn't a good fit. There was really no way to make it work. And also, SARIMA and VARMAX models assume the target variable is continuous and has a normal Gaussian. Even if I didn't have an irregular time series and there wasn't a day without an interruption, differencing every date from the 1st to 21st century would be a memory nightmare. So that's why I can't use SARIMA or SARIMAX. But we can still talk about them. They don't directly partition the data into seasons like spring, summer, or fall. They capture the seasonal effects statistically through the seasonal parameters. So how many times you difference is the number that you pass to D. So some ways that you can make it work for long-term dependencies if other assumptions are met is you can have a higher p-value. The autoregressive term p in ARIMA captures the impact of past values on the current forecast. Increasing p can give slightly more weight to past observations, but there's a trade-off. Too high a p can lead to overfitting. Then fractional integration. While standard differencing indicated by D removes trends, it might not fully account for long-term dependencies. Explore fractional differencing where D can be a decimal value. This allows for a smoother decay of influence from older observations. Then there's weighted least squares. Standard ARIMA uses ordinary least squares for fitting the model. Consider using weighted least squares with weights that decay over time. This gives more weight to older observations while fitting the model. So I didn't use VAR either because that's a vector autoregressive model because it has many of the same assumptions as ARIMA, but I wanted to. So if we want to rephrase the question to see if we could predict how many volcanoes erupt each year, I would use Poisson regression. But now we have another assumption problem. Overdispersion. Overdispersion is when the variance of the data is greater than the mean. While comparing variance and mean can provide an initial clue, it's not definitive. Consider a formal test like the Vong test or likelihood ratio test to statistically assess overdispersion and compare the negative binomial model to a Poisson model. So I'm going to use the negative binomial regression instead. This is an extension of Poisson regression that can handle overdispersion, a phenomenon where the variance is greater than the mean in the data. Output you. So let's go over the summary of a negative binomial regression model fit. The length function used is log, which connects the linear predictor of the model to the mean of the response variable, count data in this case. The scale parameter for the negative binomial distribution is estimated to be 1. The log likelihood, this value measures how well the model fits the data based on the chosen distribution. Lower values indicate a worst fit. Uh, the deviance is another measure of fit with lower values indicating a better fit. So the chi-squared statistic is used for goodness of fit test in some cases, but its interpretation might be less clear-cut for over-dispersed count data models like negative binomial regression. So the number of iterations, the model fitting process converged in 6 iterations. The pseudo R-squared, this value tries to mimic the R-squared statistic from linear regression in the context of GLMs. However, its interpretation as a proportion of variance explained might be less straightforward than the traditional R-squared. The coefficient estimates, the table shows the estimated coefficient for the predictive variable named x1. So the dispersion parameter, the estimated dispersion parameter, this value estimates the over dispersion parameter in the negative binomial distribution. A value greater than 1 indicates over dispersion. So we got nearly 6, which means the variance of the count data is larger than what would be expected based on the mean alone. And you can see from the predicted counts, it just goes with what's most likely to occur based on the past values. It's like you could have just guessed. This works for a base model, but we'll need more variables to get a more accurate forecast.